All right, let's talk about College Algebra Chapter 2, Section 2. In this section, we're talking more about functions and their graphs. And to do that, I'm going to use these notes, which were adapted from Blitzer's College Algebra 5th edition. The first thing we need to look at in our conversation about more functions is the definition of the difference quotient. And if you're going all the way through Calc 1, you're going to eventually know the difference quotient very well. But the use of the difference quotient here is kind of an exercise for us to do some algebraic manipulation. And this is a task which a lot of students I've seen over the years, it kind of ends up getting done inside out or backwards. Instead of putting A into B, we end up putting B into A. So let me give you an illustration of how this is supposed to be used correctly. The difference quotient has these three components, and we're going to look at them individually, and then we'll put them all together, and then we'll sort of sort things out. So the function that we've been given here is f of x equaling 6x plus 1, and I'm going to use that function to evaluate f of x f of x plus h. Now, as an aside, if you look over to the sort of right part of your screen, if I asked you to evaluate f of 2, what would you do? You would take a 2 and put it in place of the x, and you would have 6 times 2 plus 1. We're going to do the same thing, except with an x plus h. We're going to write 6 times, not times x, not times 2, but times x plus h. And make sure you put that x plus h in parentheses, and we'll close those up, and then don't forget the plus 1. And we could go ahead and expand this right now, I suppose. Let's distribute multiplication by 6. We get 6x plus 6h plus 1. So that's f of x plus h. The second component in the difference quotient is f of x. We already know what f of x is. It was given to us. It is 6x plus 1. And the other component is the h in the denominator, and there's nothing special that we have to do with that one. So let's take these three components and put them together. We'll work with this, and with this, and with the h. So our difference quotient equals f of x is going to go into the numerator. Let me put my division line here. F of x plus h first goes into the numerator, and that is the 6x plus 6h plus 1. And then there's a minus sign, and I'm going to do that in black. And then after that comes f of x, and I'm going to put f of x in parentheses. It's a good idea when you're substituting one thing into another thing to put the new quantity in parentheses. And here that's very important. And the h is in the denominator. It's important here because the next thing we're going to do is distribute that minus sign that I put in black. So let's do that. I'm just going to keep working my way from left to right, and then I'll wrap onto the next line. Do I want to do it that way? No, let's work our way down the page. I'll put my equal sign down here. So let's distribute. I'll put dist here to remind me that I distributed. And here's my division line. We've got 6x plus 6h plus 1 minus 6x minus 1 all over h. So we see now why the parentheses were important, so that we distribute the minus sign. I did that. The next thing we'll do is combine like terms, CLT, and this positive 6x will cancel out with this negative 6x, and the positive 1 cancels with the minus 1. All of the terms that were part of this f of x up at the top of the screen, which was this f of x, which was this f of x, once we negated it, all of the terms in f of x will cancel out as you combine like terms in your processing of the difference quotient. If they don't all cancel out, then you've made a mistake. Maybe just a little typo where the, I don't know, maybe you switched a sign or something because your I went to a different part of the problem. Who knows? But just be mindful that every time all of those terms from f of x are going to cancel out. Okay, what are we left with? I see a 6h in the numerator. Oh my gosh, that's it. That's all that's left. It's over h. Those h's are going to cancel out, and we're left with 6. So the difference quotient evaluated using the function f of x equals 6x plus 1 simplifies down to 6. Another type of function is the piecewise function, and a piecewise function is interesting because what you do with a piecewise function depends on what your input value is. In this case, if we're given an x value that's less than 0, not equal to 0, but less than 0, then we'll take that x value and we'll plug it in here, multiply it by 6, and subtract 1. However, if we're given an x value that's greater than or equal to 0, then we'll do something different with it. We'll plug it into this lower function, multiply it by 7, and add 3. And so this problem asks us to evaluate the piecewise function for 3 different values. F of negative 3. Negative 3 is less than 0, so we're going to plug it into the upper part of the piecewise function, the first piece, you could say. And we'll do some arithmetic there, and we get a final answer of negative 19. So that's for part A. Part B asks us to evaluate f of 0. 0 is greater than or equal to 0. So we'll use the second piece of the piecewise function, and we'll take the 0 and plug it in for x. Notice that I'm putting my input values in parentheses. It's a good habit. So good of a habit that I do it almost every time. All right, don't forget the plus 3 at the end of that, and we get a final answer of 3 there. And for part C, we're supposed to evaluate f of 4. 4 is greater than or equal to 0. So again, we're going to use the second piece of the piecewise function. 7 times our input value of 4. Don't forget the plus 3. 28 plus 3 is 31. And you've got your 3 solutions, and now you have a better idea, hopefully, of how to evaluate a piecewise function. Increasing and decreasing functions. So these aren't specific types of functions as much as they are characteristics of functions or characteristics of parts of a function. And yep, perfect. Okay. So a function is increasing if, as you move from left to right on the function, on the graph, if your y values are increasing, then your function is increasing. If, as you go from left to right, your y values are decreasing, then it's a decreasing function. And if, as you go from left to right, your y values are staying the same, then you're working with a constant function. The way I always imagine it is as though there's a little person. And this person is always moving to the right. The x coordinates are always increasing. The little person is always moving from left to right. And so here I can see that my little friend is going uphill, and that's why I think of it as increasing. His height above sea level is increasing. His altitude is increasing. Altitude's more for airplanes. His elevation is what I was thinking of. His elevation is increasing. And over here, I have another friend with with long legs. She's very tall. Her hair is there. And as she moves from left to right, she's walking downhill. And so this function is decreasing. And here, I always think of this as Florida because it's flat. So that's a constant function. Now, we're not always going to look at the entire function and ask, is the entire function increasing? We might only look at a particular part of it. And in this case, we're looking at it on this interval where the x values are only going from x1 to x2. And I can see that the y coordinate here, when x equals x1, is, and then I compare it to the y value of that point where x equals x2, and I see that this second y value is lower than the first one. So overall, I have definitely gone, or my little lady friend up there has gone downhill, and therefore it's decreasing. Okay, come up with whatever ridiculous stories you need to tell yourself to remember increasing versus decreasing. And then use that ridiculous story in order to answer this question. Use the graph to determine the intervals on which the function is increasing. So draw your little friend onto your graph and have them march from left to right and keep track of when your friend is going uphill, increasing. I would say that we're going uphill on this interval, and we're going uphill, or I'll say on this part of the graph, and on this part of the graph, and on this part of the graph. From left to right, we're going uphill on all of those. And I guess the next question, maybe a good way to phrase it is, when are we going uphill? The question itself says, determine the intervals on which the function is increasing. And what they're really asking us for is x values, or when is the function increasing? And the answer to the question of when is answered using x values, and I can see that these x values from -5 to -4 are the x values of those points that have increasing y values. I also see here, from here to here, I've highlighted in green, those are the x values where we're going uphill, from -2 to 0, and again from +2 to +4, those are the x values where my curve, in this case, is going uphill. Interesting is this question. What's happening right here at the top of this hill, so to speak, if we're imagining walking from left to right on this graph? When I get to the top of the hill, am I still going uphill? When I get to the top of the hill, am I going downhill? Is it neither? When I get to the top of the hill, I like to sit down and take a rest, have a look around at the view. I'm not going uphill or downhill, and in fact, that's correct. When you're at the top of a hill, or if you're at the sort of in a valley, right at the bottom of the valley there, your function is neither increasing nor decreasing. And if you make it to Calc 1 again, you'll look at that concept using some different tools. But for the moment, let's just feel informed that the function is neither increasing nor decreasing at a high point or a low point like that. And so we won't be including those x values in the interval on which the function is increasing or decreasing. So let's start listing our solution here. We said from -5 to -4 is this first group of x values. That's looking like answer B to me. And then the next red interval was from -2 to 0, still B. From +2 to +4, still B. I'm going with B. I don't know about you. I think B is the right answer. Maxima and minima. There are such things as absolute maxima and minima, but at the moment we're going to look at relative max and min, and a relative minimum, as we can see in this illustration down here, looks like the point that's at the bottom of a valley, and that's the way that I have always envisioned it in my mind, and that a relative maximum is when you're at the top of a hill. If I'm at the top of a hill, because we were just at the top of some hills in the previous problem, if I'm at the top of a hill and I look to my left, everything else is downhill in that direction. And if I look to the right, everything is downhill in that direction also. That's how I know I'm at the top of the hill, if everything else is lower than me. Mathematically, you would say that everything else in your immediate vicinity has a y value less than your current y value. That's how I know I'm at the top of the hill. Similarly, if you're at the bottom of a valley, if you're at a relative minimum, then all points nearby are going to have y values that are larger than your y value. So that's my version of relative max and min in sort of layman's terms. You're welcome to read these definitions. Good on ya, and maybe those will help to clarify something. If they don't, let them go and use my hills and valleys sort of analogy. One other thing, sorry, let me mention. If the y coordinate at this point that I've drawn right here is 4, and the x coordinate at that point is 3, and this function is called g, and I said, does function g have a relative max or relative maximum? You would say, why yes it does, because you look and you see that there's this kind of hill, and the hill has a high point. And I said, then what is the relative max? Would you answer with the 3 or with the 4? And the correct answer would be the 4. When we ask what is the maximum, what is the minimum, we're really asking you for a y value. So take special note of that, please. The follow-up question to that would be, when does the relative max occur? The answer to when would be answered in this case with the number 3. That's the input value that leads to that relative max. What is the maximum? That's a y value. When is the maximum? That's an x value. Our next little subtopic here is even and odd functions and how those relate to symmetry. There are a couple of tests right here that we can do to determine if a function is even and to determine if a function is odd. And we'll do a little example in order to illustrate that. Be aware also that if a function is even, it's going to be symmetric about the y-axis. And the best example I think to use of an even function that's symmetric about the y-axis is the most basic parabola that you can think of. This thing has what I like to call butterfly symmetry, right, or book symmetry, because it has sort of side-to-side symmetry. You can flip it over the y-axis and it lands on itself. A function that has odd symmetry, an odd function has kind of unusual symmetry. It's going to be symmetric about the origin. And while the first example that I just gave you is y equals x squared, the example that I like to give of an odd function is y equals x to the third, and its graph looks like this. This function has symmetry about the origin, and a way that I like to describe what does that mean, symmetry about the origin. It means that if you pick a point on your curve, and hopefully this will work, if If you pick a point on the curve and then you go from that point straight to the origin, whatever distance that was in whatever direction you were heading, keep going. Pass through the origin, go the same distance in the same direction, and you're going to end up at another point on your curve. Doesn't matter what point you choose, you'll pass right through the origin and end up at another point on your curve. That is origin or symmetry about the origin. Determine whether each function is even, odd, or neither. Let's just work through one of these. Let's work with g of x. We already know what g of x is. It's given to us. The other two things that we're going to need in order to do our testing is we're going to need g of negative x, and we will need negative g of x. So let's figure out both of those. G of negative x is equal to, or can be found by, right, we're taking this x that's in here and we're replacing it with a negative x. And if we replace one x with a new value, we have to replace all of the x's. That's this one and this one. So let's replace those with negative x's, and we get negative x quantity squared minus negative x. Notice that I put my new values, my new negative x's, in parentheses. And when we simplify this, we get positive x squared plus x. The other thing we're going to calculate is negative g of x. But first, let's do this first test. Let's test to see if it's an even function. The question is, then, does this equal g of x? Does it equal x squared minus x? X squared plus x does not always equal x squared minus x. The answer to this question is no. These two things are not equivalent. G of negative x does not equal g of positive x. So g is not an even function. Now we're going to make a different comparison. We're going to compare negative g of x, which is the opposite of g of x, which is x squared minus x. Right, so I just put a negative sign in front of that function, which means I negate the entire function, which means I put a minus sign in front of the whole function in parentheses, and then we're going to distribute that minus sign or that negative sign so that we get negative x squared plus x. And then we're going to ask the question, does this equal g of negative x, which we already determined. So let me put a question mark over that equal sign. Does that equal x squared plus x? In other words, does negative g of x equal g of negative x? And the answer is no. Those two are not equal to each other. No again. So g is not an odd function. So the task was to determine whether each function is even, odd, or neither. The answer is neither. It's neither even nor odd. If you would like to perform those two tests, and I recommend that you do so you can get better at plugging those things in and using parentheses correctly, I will tell you that this function right here is odd and this function right here is even. But process those tests and make sure that they turn up either true or false. That first function, f of x, do the test. Try to see if it's even. It should fail. Your left side should not equal your right side. And vice versa for function h. So even functions and y-axis symmetry, I talked to you about that. That's the parabola. But here you've got all that information together. It's even, it has y-axis symmetry, and if it's even, it's going to pass that test. If your function is odd, then it's going to have origin symmetry. The way I phrased it was I said it will be symmetric about the origin. And if it's odd, it will have passed this test. Do you really need all the other text that's wrapped around those things that I circled in red? Probably not. So if you happen to have these printable fill-in-the-blank notes, that's great. But when it comes time to prepare for your test on this material, you might want to go through and take notes on these notes and consolidate this stuff so that it doesn't have anything confusing sort of jumbled around it. Everything that's written around it is true, it just might be distracting for you. Something that we don't see very often is step functions. And this is the kind of classic example, is that our mail system uses step functions. And what they do is they say, well, if you have a package and you're going to send it, and that package weighs between 0 and 1 ounce, in other words, if it's less than 1 ounce, we're going to charge you 37 cents. And if it's over 1 ounce but not over 2 ounces, then we're going to charge you 60 cents. What if it weighs 1.5 ounces? 60 cents. What about 1.1 ounces? 60 cents. And so on. So if we graph the weight as compared to the cost to ship, well, for starters, you would never ship anything that weighs 0 ounces, and that's why there's an open circle right here. How much can we zoom in? That's as good as it gets. There's an open circle there to the right of the 37 because we're never going to ship anything that weighs 0 ounces. But you can see that anywhere between 0 and 1, including 1 ounce, that's why that circle is shaded in. So including 1 ounce is going to cost 37 cents. At 1 ounce, we've got an open circle up here, which means there's no point there. That point's already been addressed on that first interval at 1, 0.37. However, anything larger than 1 all the way up to 2 and including 2 ounces is going to cost you 60 cents, including 1.1 ounce and 1.5 ounces and 1.76 ounces. All of those are going to cost you this rate of 60 cents to ship or to mail. So again, you don't run into it very often, but you should be aware of the existence of a step function. There is I don't know about famous, but there's this kind of well-known step function called the greatest integer function. I'm not going to talk about it. You can go and look it up, watch a YouTube video about it or something. It's just too specific for our purposes, but you could go check it out. You could run into it. Chances are slim, but it's possible. Here's an illustration of it. What's the greatest integer less than or equal? What's the greatest integer less than or equal to 1.3? And the answer is 1. What's the greatest integer, the largest integer, less than or equal to 1.5? And the answer is 1. Same thing for 1.9. What's the greatest integer that's less than or equal to 1? Well, oops, I put that arrow in the wrong place. Greatest integer less than or equal to 1. Well, you're already there, as it turns out. 1 is less than or equal to 1, and it's an integer. Super. So you could keep marching through that and do that with the 2's and the 2.3 and 2.5 and 2.9. It's like rounding down to the nearest integer, I think would be a good way to describe it. 2, however, you don't have to round that down. It's already there. It's 2.0. And the graph, you can see, ends up being another step function. And that is the end of Chapter 2, Section 2. I thank you again for joining me, and I look forward to sharing with you some information from 2.3. See you there.